Can you hear me okay? All right, great. There we go. I better not touch that. I want to talk to you about what's next for Moths, metal organic frameworks, and I just want to say that following the previous speaker, I feel rather stressed. I always tell my students, there are two ways of knowing how to do a good thing. One is to know how to do a good thing, and the other is to know how to do a bad thing so that you don't do it again. And so this is an example of a bad presentation. Okay, I'd like to introduce, I think some of you may know about this new class of materials and others may have heard about them, but I'd like to introduce them as materials that are made by linking organic and inorganic units to make really a wide variety of frameworks that are in need of your expertise at this point in terms of characterization, understanding their various aspects of their chemistry. I'd like to show you how one can use that chemistry to achieve really the highest porosity ever achieved in materials, and furthermore, the highest pore openings of any crystalline porous material. Then I'd like to share with you what the future is in store for moths and how one can introduce multiple functionalities within the pores, and perhaps, if we can stretch our imaginations a little bit, design sequences, just like sequences within DNA, but sequences within moths to code for particular properties. And then I'd like to update you on some activities and how a lot of this is related to a lot of the great work that's being done at the Molecular Foundry. Let me introduce metal organic frameworks in the following way. If I take nanoparticles, let's say that they're shaped as cubes with 6 nanometer size on an edge. If you calculate the surface area of such cubes, you find that it's around 2,000 square meters per cubic centimeter. Okay, and that's not an achievable surface area in nanochemistry, because when you make these nanoparticles, they adhere to each other, preventing access to the surface. And so what really metal organic frameworks have figured out how to achieve this is to use hollow cubes and link them together. If you do that and you calculate the surface area provided by these scaffold, let's say the scaffold is based on phenylene units, you find that in fact you should get around 2,000 square meters per cubic centimeter. And indeed, if you could make the scaffolding architecturally stable, it should be possible to not only get that surface area, but of course that surface area would be accessible. So that's really the idea. And in order to bring this idea to fruition, the way we think in this kind of chemistry is that we think of any kind of structure that we imagine as composed of two components. One component is a branching point, and the other component is the link that joins these branching points together. And I was trained as an inorganic chemist, so to me this is nothing more than a metal ion or a cluster of metal ions that have a definite geometry, in this case a 6-way intersection. And then our idea was to link these inorganic units with organic units to produce this extended structure. And very early on, we chose components like terephthalic acid, the main component of plastics, and zinc oxide, the main component of sunscreen, to make the first metal organic framework that's really in the image of the hollow architecture that I showed you early on. It's made from metal oxide intersections and organic units linking those together, with the yellow ball indicating the space that would be accessible should these architectures be stable. And indeed, we showed many times over that these are architecturally stable and gases and molecules can diffuse in and out of the pores without affecting the architectural integrity of the framework. But more importantly is that once you know the conditions under which these metal oxide units could be made and assembled, one can vary the organic units to include various functionalities. And therefore, if you think about a reaction happening inside the pore, now you have a way to fashion the interior of the pores by way of functionalizing the pores. Also, another very important thing we discovered early on was that you can expand the metrics of the system without changing the underlying topology. And that's quite powerful because it allows you to design. Generally speaking, with solid-state materials, when you try to change, let's say, their functionality or their metrics, you actually make new kind of structures based on new topologies and destroy the original architecture. And here we preserve the architecture even after functionalization, after expansion of the pores. This is what the material would look like. It's an extended structure, and the yellow balls indicate almost 60% of the crystal is just open space. When we synthesize the material, the space is filled with organic solvents. And so to fully characterize the porosity of this material, we took single crystal of, let's say, MOF5 in this case, and did single crystal X-ray diffraction at 30 Kelvin. The crystal was evacuated without losing its architectural stability or without introducing a lot of defects as to prevent its monocrystallinity. And we examined this by single crystal X-ray to find that indeed the framework is maintained in the absence of guests. This is the thermal ellipsoids at 90%. This is a structure that's done at 30 Kelvin. But the key here was to understand where, let's say, a gas molecule, when it diffuses through the pores, where does it sit in the framework? Because as chemists, we know that if we know the binding site for molecules, we can functionalize or play with the electronics of that active site in order to enhance, say, the absorptive properties. And in this case, MOFs already have been viewed as great materials for hydrogen storage, natural gas storage, and carbon dioxide capture. Well, we found that, in fact, when you start introducing gases like argon or dinitrogen, that you do find localized electron density for argon and nitrogen on this metal oxide groove. And in fact, to our surprise, we found that not just that the metal oxide has many different metal, gas binding sites, but also that the organic, both the face of the six-membered rings and the edges, act as adsorptive sites for in metal organic frameworks. This was very exciting because it meant that everything in the MOF potentially can be an adsorptive site. And so that could give us maximum adsorptive capacity. And the fact that the edges are also adsorptive sites made us think more about how to design structures that are replete with open faces but also open edges. And so the more exposed the edges are, the higher your surface area is going to be. And the nice thing about MOF chemistry is that you can take those metal oxide branching units and link them up with organic branching units to make extended structures that are replete with open faces and open edges for gas molecules to sit on. And this, when we made this, we called this is a new net, and we called it the queen of MOFs. Because we didn't think we could make a more porous structure than this, since the surface area, as you can see here from the nitrogen adsorption isotherms, here the nitrogen goes in and then fills the pores, and then we can take it out. And this is a signature, this knee, sharp knee, is a signature of permanent porosity of the structure as gases diffuse in and out. The surface area was 4,500 meters square per gram. Now we are able to evacuate the pores very efficiently and get even 6,000 meters square per gram. That's around 4 times the previous record held by porous carbon and by other porous materials, both crystalline and non-crystalline. In this case, moths are crystalline. They have well-defined structures, and as I showed you, the components of which can be varied. And so then the race has begun or began after that report on an international level to try to beat that record. And so in my own laboratory, we made some of these these links and tested their porosity, predicting even higher surface areas. And you can see here, not only can we make the queen of moths, which we called Moth 177, but also its expanded analogs and other structures, again with maximally exposed faces and edges. And you can see here that our original Moth 5, which has a surface area of about 3,000 meters square per gram. This is Moth 177, and this is the most recent Moth, Moth 200. You can see here gas uptake and evacuation of the pores with a signature isotherm. The structure looks like this. This is Moth 200. This is supposed to be rotating on the screen. But the Langmuir surface area is 10,000 meters square per gram. And that's about several football fields for every gram of material. So if I take a gram of material, which is no more than that high, and I unravel it to its atomic level, it could cover a couple of football fields. And that's really the space that is available to bind gases or to store gases like hydrogen and methane and carbon dioxide. The key here, that is unlike other porous materials, here the materials are entirely composed of edges and open faces of six-membered rings, and therefore the entire structure, everything you see in the structure is a binding site for gas molecules. And so this really started an avalanche of studies of combining organics and inorganics, and now, just this year alone, over 3,000 moths have been made and reported. And so I mentioned the race for high surface area materials. These are the traditional materials some of you may know about, zeolites and silicas and porous carbon. And these are the moths variously shaped in order to maximize their surface area. So the most recent study about a year ago or 2 years ago now, Moth 200 is around in excess of 10,000 meters per gram. Can we make materials that have even higher surface area? And the answer is yes. If you go to links that are not phenylene units, but let's say acetylenic units, you should be able to get, if you do that for a structural motif like this, you should be able to get almost 18,000 meters square per gram. And so this is ideal materials to store gases, and I mentioned hydrogen and I mentioned carbon dioxide, and both of those moths figure prominently in those applications. But I want to talk about methane, because methane is a transitional fuel. It's cleaner than oil, and it is one that is already in the market with moths. It's 2/3 of our fossil fuels are stored in natural gas, and it's the least used fossil fuel. It will be used more and more, and already chemical companies are focusing on that. So we work with BASF, the largest chemical company in the world, to apply these materials not just for gas storage but for other applications. In this case, methane storage in Moth 177 at room temperature shows an exceptional uptake capacity. This is the tank, behavior of a tank, a vessel in your laboratory, where we're plotting here the amount stored in that tank versus pressure. And if you look at the same tank filled with Moth 177 powder, this is the total uptake of natural gas without changing, let's say, a pressure or the temperature. So at any given pressure, you're storing at least double the amount that you would store in a tank that does not have a moth. And this was quite compelling as to do this really brave experiment, which is to equip an automobile with a natural gas moth tank and drive the automobile all over the world to show that indeed, no matter where the gas is produced and used, and without purification of the natural gas. It's the natural gas that is supplied to the methane moth fuel tank is that is received in the kitchen at these locales. And at the end of this experiment, which spanned 28,000 kilometers, the moth only lost 10% of its porosity. And so really this is very exciting because as of today, the moths have been tested by VSF for over 100,000 cycles and for the lifetime of an automobile. And at the end of the lifetime of the automobile, the moth material, first of all, never has to be changed, never has to be regenerated as you fuel and defuel or use the fuel, but it can sit in the car for as long as for the lifetime of the car. And then at the end of this, one can take the solid, add strong acid, dissociate the components into the original components, and reassemble them into that moth or even other moths. So it is potentially a zero discharge process. The moths originally were not stable, highly stable in water, but recently zirconium moths have shown exceptional chemical stability. So moths in general are very stable, thermally stable up to 300 or to 500 degrees C. That is routinely known for moths because they're made from very strong bonds, metal-oxygen bonds and carbon-oxygen bonds and carbon-carbon bonds. But the challenge for a while was, could we have them sit in water? Could they be prepared in water? Could they be made to be chemically stable in acid and base? And finally, that dream has come true with these zirconium moths. You can see a variety of them could be made, and indeed, one can put them in aprotic polar solvents and water and acetic acid without changing their underlying ordered structure. These are a couple of moths we recently reported that are made from zirconium building units and organic building units. Now, I intentionally have not said anything about the guests that are in the pore when you make the material. That's because we know very little about them. And so this is an opportunity, I think, for this audience to collaborate with the moth community on trying to figure out what is the role of guests in the pores as the material is being made. We also don't know anything about the nucleation of these crystals while we are at the seeding and crystal growth intervals. Again, that's an opportunity to do studies that delineate that and trying to influence what kind of frameworks could be designed. So there's a lot of opportunity there. We know a lot about how to make the frameworks and how to functionalize them. We know very little about what goes on in the pores aside from where gases bind. So there's a lot of opportunities there. So far, the moths I've discussed have pores that are as large as, let's say, 1 phenylene unit or 2 phenylene units stuck together. But to really be able to bind molecules much larger than that, let's say proteins, we need to be able to open up the pore opening to allow very large molecules to pass through and be able to perform chemistry on such molecules. So in order to do that, we moved away from the discrete metal oxide building units that I've been talking about and use rod-based building units, as you see here. You could use rod metal oxide units, in this case zinc oxide units, that are linked by phenylene, and the rods here are arranged in hexagonal fashion, and they are linked by organics to make a one-dimensional porous structure. It turns out that this actually is another fertile ground for making moths, and in fact, there are many different ways of arranging rods, not just in hexagonal form, but in cubic form and Kagome lattice form. All these rods can be arranged in the way you see here, using the color and pointing into the frame, into the board, in this case pointing opposite to each other, but always linked by these gray units, which would be the organic units. So all these allow us to overcome a difficulty with moth structure, which has been the interpenetration, which as you open the pore, oftentimes you have frameworks that catenate or interlock mechanically so as to reduce porosity and make more stable structures. Well, we made some of these rod-based structures, and I want to focus on one of them, which is the hexagonal arrangement of metal oxides linked by organic, and that's MOF 74. We reported in 2005. In MOF 74, you have a rod of metal oxide. This could be zinc oxide or magnesium oxide, and the rods, again here pointing into the screen, linked by organic unit, in this case this phenylene unit. It turns out this is one of the stars for hydrogen storage and has really very interesting carbon dioxide capture properties, but it does not interpenetrate, and so it was a nice structure to expand its pores. And so this is the original link for MOF 74, and we collaborated with Fraser Stoddart to make these links and adding incrementally 1 phenylene units or more as you go along. And sometimes to enhance the solubility of these links to make the ultimately the MOF in crystalline form, we needed to functionalize them with organic units to enhance their solubility by breaking the pi-pi interaction in the solid. But nevertheless, it turns out that a very clever student I have, his name is Hekshang Deng, led a team of researchers in my group to actually be able to make a dream come true, and that is to be able to link a rod-like link in this of 11 phenylene units, which I've never dreamed that we would succeed in doing, to make a MOF out of that, and of course very large pore aperture. So the pore aperture, let's say for the original MOF containing 1 phenylene unit, is 14 by 10, and I'm going to zip through these. 2 phenylene units, you go to a pore aperture of 20 by 16, and you can see a very nice sharp XRD. These are not single crystal structures. They're based on powder diffraction data. This is the experimental. This is the predicted. And since we're only expanding the pore, we can predict what the XRD looks like. But I'd like you to focus on the XRDs because they become lousier and lousier as the pores become larger and larger, because most of the crystal or most of the material is really disordered guest molecules that are floating in the pores. And so 3 phenylene units get you to 27 by 22, and the XRD is still sharp and nice. 4 phenylene units, 33 by 28, and now you can see slight broadening here beginning to creep up. 5 phenylene units, 41 by 35, and that was the previous record for any porous crystal in terms of pore aperture. And so we have now 6 49 by 41, 6 phenylene units, and 7 phenylene units to 58 by 49, 9 phenylene units, and very lousy XRD, but nevertheless, I think we can say convincingly that we have that framework. And then 11 phenylene units to get to 98 by 85 pore opening, and a very broad XRD, but again, we have the 110, very indicative of that framework structure. The opening of the pore, which is the object here, has 282 atoms. That's the mouth of this porous crystal. And it turns out that, I won't go through the details of this, but it turns out that they have predictable gas absorptive behavior. We don't really want to expand the pores for gas storage, but rather for the binding of large molecules. Since for gas storage you have to increase the surface area and make sure that the pore size is on the order of the size of a gas molecule. So indeed, the largest, or some of the largest members of this series take up myoglobin, and here you can see the uptake of myoglobin from solution or depletion from solution. We can also bind proteins as large as GFP into the pores. So again, a lot of things could be done here. Again, in this community, would be nice to put proteins in the pores that are very difficult to crystallize, but maybe can be ordered and examined within the pores of moths. So what has been done here with moths is that we have transformed really the chemistry of linking building units together from the weak bond regime into the strong bond regime, which previously people thought that is inaccessible regime, because as the bonds get stronger and stronger, the crystallization problem becomes more and more challenging. And so, indeed, I would like to say that while building structures from weak building units, that's the domain of supramolecular chemistry, but the control of the strong bonds, as we have shown with metal organic frameworks, and some of you may know we've extended this to imidazolate frameworks and covalent organic frameworks that don't have any metals in them, and we call this kind of chemistry reticular chemistry, just to emphasize that it is about the control of the strong bond and making of robust materials. The making of robust materials really extends to the future of materials synthesis and materials discovery. And let me just show you that if you step back and you think about all the materials that have been made and used within this century and last century, they've all been based on one kind of building block linked by strong bonds, two kind of building block, or three kind of building blocks. This includes polymers and zeolites and alloys, silicon, metal oxides. A lot of the useful materials have been based on either one, two, or three kind of building units, and rarely on 4 or 5 different kind of building units or more. But we know from biology that multiplicity of different kinds of building units gets you really a system that has information, that can convey information. But also it gives you tremendous functionality, control over making highly functional materials. But we can't build our entire world out of proteins and RNA and DNA. And so we need the robustness of the materials that I'm showing here that are linked by strong bonds and the control of the strong bond to make those robust materials. But we do need to concept transfer from biology how we can take this intelligent design from biology and concept transfer it into synthetic materials. The reason I show this is to show that in just from up to 3 kind of building units, we've created an immense richness in chemistry, and that more richness should be achieved by adding more and more building units. And this takes the form, so I would say that the materials that could be designed, that still could be designed, are far more vast than what we have already seen. And the chemistry and the tools necessary to really explore these materials beyond are different than what we have today. And I'll show you one problem of how this manifests itself when you have multiple building units. Once you start thinking in terms of heterogeneous kind of building units in one material, you immediately face not just the excitement of what kind of materials you would be able to make, but also the challenge of how you're going to make them and how you're going to characterize them. And I just want to show you one example of how challenging this problem can be, but also that we have hope that we can overcome this issue of making and characterizing. So here's a moth, let's say, where the backbone, we know how to make the backbone. I think I've convinced you that there's enough moths out there that where we have control over the branching points and the organic links. But in my world, in inorganic chemistry or in molecular chemistry, every time you have a system that has many different components, as this implies, the result has always been believed to be a mixture of phases, each phase containing one of these, rather than one phase containing a mixture of those components. And that's really what we want to aim for. We want to create environments within the moth that are decorated by many, many different building units, just like, let's say, active sites of enzymes. And also use that organic functionality to bind metals in many different kind of coordination environments and many different metals. So we're talking about the concept of heterogeneity within order. So this is not a messy system where you have a heterogeneous amorphous material. This is really an ordered material, but the heterogeneity is coming from these functionalities that are covalently linked to the framework. We call that controlled complexity. And so this could be done. You could take the same original phenylene units I showed you for MOF5 and functionalize it with many different functionalities and incorporate all of them within one structure, because metrically they are the same and the functionalities are the same, the linking functionalities. And so the organic functionalities hanging off the phenylene units, as long as they don't interfere in the synthesis, you can incorporate them into the structure. And we know a lot about them. We know what they are. First of all, we know we have an ordered backbone, but we know that we have disordered functionalities. The functionalities are covalently linked in the ortho position, but we cannot decipher what is next to what. We know that the access to these functionalities through porosity is possible. We know the ratio of the building units through carbon-13 NMR. And we also know how to vary the ratios of various functionalities. So we have a lot of control over the composition of the functionalities. We know the ratio of functionalities. We know exactly where they're pinned onto the framework. But the key here, and we also know that our structures are homogeneous. If you take a crystal and you chip off the crystal, in different fragments, you see the same ratio of functionalities from each fragment. So now comes the big question is, when you have a crystal like this that has 8 different functionalities decorating the pores, and you're a substrate or a molecule diffusing through the pore, you're seeing the different functionalities, but what you can't figure out is what is next to what. What is the sequence of functionalities? So it's not a random mixture, statistical mixture of functionalities, because within each pore, okay, within each pore you have ligands or you have functionalities that bias what comes next to them, just because they might be bulky or they might have different pKa for that particular link. So the system is biased to the point that, in fact, I believe that there are sequences of functionalities, just like you have sequences of nucleotides in DNA. Here you have a backbone, a very robust backbone onto which you have these functionalities that convey sequence information. And so we have a collaboration with Jeff Reimer in the chemical engineering department at UC Berkeley. And there we are now just exploring the idea of looking at spin transfer decay experiments using 2D NMR to find out what might be next to what. And it's not, it's a very rough right now, but it gives us good distance information as to what functionality is next to what. And the question we're trying to answer is, do we have aggregation of functionalities in a crystal in this way on a nano size, or do we have a thoroughly mixed functionalities? And really the evidence, the preliminary evidence, show that in fact some functionalities like to aggregate within the pores and others like to be thoroughly mixed. So now I want to try to say the following, is that think about the interior surface of the crystal within the pores as a tiling, and that tiling has islands of particular functionality separated by other functionalities. And think about the various things that one can do if you can control the size of these islands and control the sequences of these islands within the framework. The reason this is very exciting is because when you have a structure, let's say, that has a mixture of 3 functionalities, it performs 400% better in, let's say, in this particular reaction of capturing carbon dioxide from a mixture of carbon dioxide and carbon monoxide. It does 400% better than the system that's not mixed. And it's not the sum performance of the parts. It's really much more than the sum of the parts. So there is something going on within these pores that allows the material to selectively capture carbon dioxide in a much better performance than any of the components or the sum of the components. The idea of mixing functionalities can be extended to also mixing metals within the pores. That the backbone of the material of MOF74 that I showed you we can introduce different metals to make, let's say, moth alloys, backbones, and you can put 10 different metals, maybe more, within the pore. So how are they arranged, and what sort of chemistry that arrangement produces? Again, we don't know the arrangement of these metals, but this is an ideal problem that we are discussing with people at the ALS here. Think now about functionalizing the pores and then attaching to those functionalities metal complexes that are used in catalysis. So instead of having a step-by-step catalysis, why not put, let's say, multiple catalysts within the pore covalently linked to the framework to carry out cascade type of catalysis? So a lot of these are opportunities for research, and these are really not very well characterized systems as far as how are these arranged with respect to each other within the pores. The idea of heterogeneity within order, as I have shown you in these examples, really extends much more than just moths. That if you look at this example, done in my group in Japan, if you want to make a metal complex from many different metals and then arrange those metals in a particular sequence, inorganic chemists tell you there is no such way. But there is a way if you try to couple that with the Merrifield synthesis method, where you take the amino acids, put chelating units on there, and these would be your building blocks. You bind metals to them. Now you have metallated building blocks, and you use the Merrifield synthesis of peptides to hook on each metal complex in the sequence you like. And now you've got a metal complex from many different metals arranged in very specific sequence. We could also do, that's another example of heterogeneity within order. Another example of heterogeneity within order, here's a crystal of MOF5, and here's a crystal of MOF5 riddled with holes. But here's a crystal of MOF5 where you have a heterogeneous mixture of pores, macropores and mesopores within the ordered system of micropores of moth, which this study was done in a group that I'm involved in Korea. And then you can go beyond that and say, well, how do we design systems that have really this kind of arrangement? You have the same shape repeated, but repeated with different metrics in the same system. How do we make these systems is, again, that's a challenge that we need to address. So far, I've really gone through the chemistry of how you build structures from covalent building units. And I have shown you the challenge of how are we going to figure out how these functionalities are arranged in the pores, and whether if we have a way to figure out the sequences of functionalities within the pore, could those sequences be designed to code for very specific properties? I have shown you other examples of how heterogeneity within order manifests itself. And also, you'll hear from Delia Milliron on Wednesday about how this concept really is at the heart of the mesoscale that the DOE has been exploring in the community. A lot of this chemistry really goes beyond my group at this stage, and it's difficult to imagine that one single group or one single institution can really exploit this broad area that I call the molecular beyond. And therefore, I really feel that the molecular foundry, which I direct at this time, is a perfect example of an institute whose scientists work in a way that would really bring a lot of the chemistry, a lot of the challenges that I have shown you to fruition in terms of the making of these materials. At the foundry, we have it's a building of 6 floors, and it spans many different fields. But a scientist in any one of these floors actually moves around the floors when they are carrying out a project with a user. And so we have these specialties, and we have about, let's say, 24 scientists personing these facilities, and at any one time we might have 100 to 150 users that are collaborating with our scientists. But this is the power of the foundry, and this is why I think this problem of heterogeneity within order is ideally suited for this environment. Is that you have the users coming into the various floors where essentially their projects are managed, but they enter a sort of a chaotic world of research where there are points of intersection between floors through the scientists that are carrying out these projects. And every once in a while, we found that, in fact, these collaborating points with users and amongst the researchers at the Foundry, they become very strong points of science. And they are the cutting edge. These problems are the cutting edge of what we call threads. And these threads not only pass through the floors, but also pass through our capabilities that are shown here. The threads that we've identified our strength in at the Foundry is mesoscale assembly, shaping nanolight, porous crystals, bio-inspired nanomaterials, dynamics at interfaces, and the rules of design. And so really what the Foundry does very well is break down the barriers between specialties and actually get down to solving the problem. That's why I have a lot of hope in that the Foundry, and I hope in increasing collaboration with ALS, we can address this issue of making materials in this regime of the materials beyond. We have, within just the last year, have increased to record numbers the number of users of the Molecular Foundry. These are badged users as defined by DOE, and these are the total number of users ranging from samples and instrument use and other people that might be participating in projects. I can't go over every single project that is going on at the Foundry, but I want to highlight just a couple of or three very quickly to show you really that these early career scientists are now becoming or have developed really mature and established groups that are capable of bringing to the forefront some really unbelievable developments. Here's one of the developments from our nanoimaging facility, a project from Jim Schuck and Alex Weber, where they developed an advanced near-field probe they call the Campanile that squeezes light to a nanometer scale and allows you to acquire data without background and allows excitation detection through the same probe, so that something that you see with SEM in this way, you can actually look at it and see the heterogeneity of this indium phosphide nanowire through this innovative probe. We have individuals such as Gary Wren who have invented ways of taking electron images of proteins and analyzing them so that they can figure out exactly the topology of those proteins. And some of these proteins are not easy to crystallize in any or figure out from crystal structures. A very recent and exciting development is the ability to strip nanocrystals of their coverings. And this is done mainly by or under the leadership of Delia Mill-Iron and Brett Helms, where they have been able to figure out a way of routinely stripping nanocrystals off these capping organic units and assemble and allow really the chemistry to go beyond what has already been possible for nanocrystals. In this case, assemble them into very large assemblages of porous materials where the building units now are nanocrystals. Here, this is showing the pores, and here you can see, I'm not sure if you can see the nice electron diffraction for each of the nanocrystals. A lot of the materials synthesis is possible through this high throughput technique, and we have many different equipment to do this in high throughput mode, both in terms of surveying the various compositions for a particular material, but also to be able to have in high throughput form bulk materials. We are also adding to the Foundry now the chemistry that I showed you with metal organic frameworks, which when I came to the Foundry many have already been exploring it. So now this would be available for users in terms of high throughput crystallization of MOFs. But really the motivation here is how do we at the Foundry make very unusual materials and make them for the first time. Here's an object for our synthesis. Is how do you, I discussed with you a lot about how do you connect building units through covalent bonds. But there is another way to do it. And that is through interlocking, mechanical interlocking of molecules. So could we use mechanical bonds to build extended structures? And what sort of properties will these materials have? Where, in fact, let's say the mechanical behavior of this material involves breaking of very weak bonds, but without breaking the covalent bonds that make up the material. So we have a lot of ambition at the Foundry to create really wonderful materials, but also we really need the collaboration with facilities like the ALS to figure out a lot of the intricacies of what's going on within understanding the chemistry of these materials. So I want to acknowledge the contribution of my group for the research on moths, and also the funding on moths was offered from these funding agencies, and thank you for your attention. Right. So I didn't talk about the kinetics of substrates or gas molecules going in the pores and coming out, and that can be controlled first by varying the pore size of the crystal, but also functionalizing the pores with bulky groups. So we've done recently. We published an article, and many people have, at trapping organic molecules or fluorescent molecules in the pores, and then triggering the opening of the pore and controlling the kinetics of its evolution from the pores through light activation. So there's a lot of work that's being done in that way, but it is by no means a well understood, what is the mechanism of how this happens, because in some of these frameworks, the links do rotate, and they have a very specific way to carry out dynamics, just in terms of their own movement. So there's a lot of that has to be really deciphered. But yes, you can control the kinetics, and that's an important part of the hydrogen storage, carbon capture, natural gas projects. Yes, so there has been a lot of preliminary work, I would say, done on impregnating the moth with nanocrystals of palladium or platinum or other nanocrystals for nanogold crystals, and then carrying out, carbon-carbon bond formation catalysis. So there's a lot of that work that is being done. A lot of other work which is being done is to trap the catalyst in a ship and bottle kind of approach. Okay, and both of those, I would say, in both of those approaches, people have observed, let's say, better selectivity, better chiral enantiomeric purity of products and things like that. But there has been no truly spectacular results, and I think, because in catalysis, you really need a well-defined environment for the active site. And I think the approach that is now being contemplated in the community is the one that I showed, where you covalently put a metal complex covalently bound onto the framework. Then you start playing with its electronic and steric, which is very important for catalytic activity. And this has not been done. So I think there is a potential there for getting unusual, or a incremental improvement in catalysis is much higher. The nice thing about, let's say, what I call the MTV approach, the multivariate approach, is that you can functionalize your link with a catalyst, But then you could also add that link without a catalyst on it, and that way you have a way of titrating into the structure your catalyst. And so that's very important sometimes for the activity of the material. So a lot of the basic science of making the structures or the advanced research for the structure is really been done, and now it's just tweaking of the interior of the pores to get, to get to better catalysis. It's typically it's just a release of pressure. So you're storing the gas at 60 bar or 80 bar, and then just to release it, you just release the just under vacuum. But yes, it could be thermal activation as well. By slight heating to 30 degrees C, you can do the same.